So we have two types of simple machines left to talk about. They are the pulley and the lever. So a pulley, we've all probably seen a pulley before. A pulley is basically a wheel with some sort of rope or maybe even a chain or a wire that goes over it, loops across it. And it can be used and set up in lots of different ways. And the way it's set up will determine its mechanical advantage and how it is helpful. So for a pulley, the way that we determine its ideal mechanical advantage is we simply count the parts of the rope that are supporting the weight. So if only one part supports the weight, it's mechanical advantage 1. If 4 parts of the rope are supporting the weight, then it's 4.
Wait, how do you know?
We'll review that. Okay? So there's 3 types of pulleys. The first one here, this is called a fixed pulley. And the pulley doesn't move. The pulley is like attached to something. Okay, you have a rope that loops around the pulley and then comes down, and that's where you attach the weight. So you pull down on the rope, and obviously the weight lifts off the ground. A fixed pulley like this has only a mechanical advantage of 1 because there's only one rope, part of the rope, that's supporting this weight. This isn't supporting the weight. Only this rope is. So what does that mean if it has a mechanical advantage of 1? So we've been saying if it's a mechanical advantage of 4, you can use 1/4 the force. But what does a mechanical advantage of 1 mean? How much?
The force is reduced.
The force is what?
Is it reduced?
Yeah, that it doesn't allow you to use any less force. So what exactly does it do? So why would you bother to use this type of machine if it doesn't allow you to use less force? Jonathan?
Instead of like lifting it up off the ground like this, you can just pull.
Yeah, this is one of those simple machines that transfers your force from one direction to another. So you can lift an object by pulling down on this rope. Okay? So this could allow you to do a couple different things. First, if you need to lift an object much higher than you could reach, you can use a pulley to lift it all the way up there because you're just pulling down. You can stand there. You can also use your body weight to pull down on it, which makes it a little bit easier. So that's what this fixed pulley is. It changes the direction of your force, not the amount of force. So the actual mechanical advantage of this pulley, if this is 100 Newton mass, and we have to pull with 100 Newtons, then the mechanical advantage would come out to be 1. Now, does anybody see an error? Would this match up with reality if I'm actually using that pulley? Why not? Herschel? Oh, throw your hand yourself. Why would this probably not work out in real life? If this mass was 100 newtons, I would not be able to pull with 100 newtons and lift that. Ashley? If let's say it was strong enough. Nicole?
You would need more effort to pull down.
Yeah, why?
Because
Theoretically, I should just use the same effort, but it wouldn't. Nicole?
Because of the friction that's going on the wheel.
Yeah, there's some friction around the rope, around the wheel, where the wheel's spinning, and that's going to use up some energy. So I'd have to probably pull with a little bit more than 100 newtons of force. Okay? All right, so that's called a fixed pulley. Another type of pulley is a movable pulley. That's shown down here. So in a movable pulley, the pulley is down near the bottom. Usually the weight attaches directly to the pulley. And then you have a rope that loops around, and you lift up on the rope here. So how many parts of the rope are supporting this weight when I use this type of pulley?
That doesn't make sense.
Nicole? Yeah, this is supporting the weight, but also this is supporting the weight. The weight's being supported by both of these parts of the rope, has a mechanical advantage of 2. Okay? Excuse me?
What is this called?
This is called the movable pulley. That one. Okay? And so the movable pulley gives me a mechanical advantage. If this is 100 Newton mass, I'd have to pull up with around 50 newtons of force.
Wait, what?
What's that?
How would you like move the object?
Because you're lifting up. As you lift up on this rope, this pulley lifts up and the object's attached to the pulley.
Oh,
We'll set these up tomorrow. I'll show you some actual
So the other
examples.
string's connected to something, and then you can
Yes,
go.
this is connected. You see your slip. Emily, a question?
You answered it.
Okay. All right. Here, this is another example on this crane. This is a movable pulley. Okay, it's attached up here to the crane, lifts up this, and it reduces the force you use by half. You use half the force to pull that up. And then, your question, Nicholas?
How much will the test, like, how long will it be?
What's that?
Like, how long will the test be? Like, is it going to be long?
Don't worry about the quiz right now. Let's focus on this. All right, our last type of pulley is the combination pulley. It's made of some fixed pulleys and some movable pulleys together. And here's an example. Now, you can set this up in different ways. You can have multiple pulleys. You can have multiple ropes supporting it. So you can set it up in different ways. For example, here we have a rope that goes over a pulley, loops around again, and then loops around down here and connects here. So we have multiple ropes here, parts of the rope, it's all one rope, supporting this weight. In this case, how many parts of the rope support it? Yeah, 4 parts of the rope. 1, 2, 3, 4. So again, if this is 100 Newton mass, weight, I'm only going to have to pull with 25 newtons of force. Has anyone ever used a pulley like this? Sometimes you'll see them like in an auto shop. They sometimes have them with chains in the bay to help like lift an engine out of a car.
Yeah.
Sometimes they have an elevator. If you've ever seen like the workings of an elevator, it has, you know, a big pulley system, a crane, and what it's allowing the force to be reduced significantly to lift a very heavy object. But if you can imagine, when I pull on that weight, what's the trade-off? Yeah, the trade-off is always the distance. To lift that weight up this high, I'm going to have to pull that rope a lot to lift it off. So I'm using less force, but I have to pull with a greater distance. So those are pulleys. We'll set some up tomorrow for you to use and experience. All right, and then our last simple machine is the lever. And a lever is, it's basically a rigid object, a rod, a board, that pivots on something that we call a fulcrum.
It's floating. Is that one of the weights?
All right, so that's what a lever is. And often we can use a lever to multiply our force. When we talk about levers, we can set up a lever in 3 different ways. And they're called different classes of levers, a first, second, or third class lever. So the parts of a lever first you have to know. So there's the resistance, which would, look at my lever I have up here. Where's the resistance?
The part that's facing up on our right.
Here?
Yeah.
No? That's not the resistance. Nicole?
Where it's like to.
Yeah, it's this weight. This is the resistance. This is the fulcrum. Where I'm going to push on the lever is the effort. Okay? So, we can identify the type of lever, the class of lever, by looking at what's in the middle. So now in this lever, what's in the middle? The fulcrum. Okay? That's a first class lever. If the fulcrum is in the middle, it's a first class lever. If you remember the word free, it can help you to remember. Because it's a first class lever if the fulcrum's in the middle. Second class lever if the resistance is in the middle. Third class lever if the effort is in the middle. Okay? So, what type of lever is this? What type of lever is this, Joey? Okay, this is because what's in the middle? That's the resistance. This is the person's hand.
Oh, that's
a third class lever.
Yes, that's a third class lever. The effort is in the middle in that case. What about this lever? What class is this lever? Courtney?
Second.
It's a second class. This is the resistance. And this last lever, Olivia?
First.
It's a first. Here's the fulcrum that's in the middle. It's a first class lever.
What's the whole point?
Excuse me?
What's the whole point of like the third class?
We're going to go over those
It
right now.
doesn't make sense. Like,
Yeah, the
why
third
does-
class lever, we'll get it there. But let's take them one. Let's take them one at a time.
What was fourth E?
There, it does nothing. Just helps you remember free because it then makes it work. Otherwise, it'd be fret. And it's not as easy to remember fret as it is to remember free. Okay, first class lever. If you've ever been on a teeter-totter on a playground, that's a first class lever. Okay, you have the fulcrum in the middle. Okay, and then you have the resistance on one side, the effort on the other side. Here's a diagram of one. So first class lever is a fulcrum in the middle, and as the fulcrum gets closer to the resistance, the mechanical advantage increases. So if I put this fulcrum closer to this resistance, I barely have to push on this at all to lift the weight. Okay? That's a very high mechanical advantage. If I move it back here, I need to push harder. I need to use more effort to lift that resistance. So examples, a teeter-totter, a pry bar, a bottle opener, these are all types of first class levers. To calculate mechanical advantages, again, the formula doesn't change. It's effort distance versus resistance distance. Where we get those distances, effort distance is from the fulcrum to the effort. Resistance distance is fulcrum to the resistance. So in this case, effort distance is 150 centimeters. Resistance distance is 50 centimeters. And that would give us a mechanical advantage of what? 3. That's on the bottom. It's getting cut off, but that's ideal right down here. Mechanical advantage is 3. To calculate actual, the formula again stays the same. Resistance force over effort force, but then we're measuring forces. The resistance force in this example was 50 newtons. I'm pushing here with an effort of 20 newtons. And that gives us an actual mechanical advantage of 2.5. So make sure you write that in down here. Again, less than the ideal because of friction. A second class lever, like we said, has the resistance in the middle. And as the resistance moves closer to the fulcrum, mechanical advantage increases. An example of this, I don't know, around the holidays, does anyone's family get that weird assortment of nuts?
Yes.
And then you got to use a big nutcracker. Nobody ever eats them. When I was a kid, I just liked to crack them. I never ate the insides. They're always weird. But anyway, that kind of nutcracker, that is an example of a second-class lever. If you imagine, the fulcrum is here. The nut you put in there is the resistance. And then where you squeeze down here, that's the effort. So resistance is in the middle.
Oh, like this hand crunch thing.
Yeah. Makes that sound too. Again, the formulas are the same. Effort distance over resistance distance. Fulcrum to effort. Fulcrum to resistance. In this case, it's 120. It's the effort distance. 40 is the resistance distance. This gives us a mechanical advantage of 3. And again, so the way that nutcracker works is the force we apply here is multiplied 3 times here, and that's why we're able to crack that nut fairly easily. Actual mechanical advantage, we just use the forces that are involved. 70 newtons versus 30 newtons. Okay, so I could set that up here too as well with this type of lever. If I put my resistance in the middle, I could lift up. It's very easy. But again, what's the trade-off? How much is my hand moving versus how much is the resistance moving? Not much. All right, we got to finish. Don't put your stuff away. All right, the last lever is the third class lever. Oh, wheelbarrow also. Fulcrum is the wheel. Resistance is what you put in the wheelbarrow. Your effort's the handle.
What is the answer? How do you have
What's that? Oh, that's 2.3. All right, third class lever has the effort in the middle. But it does not increase our force. It doesn't multiply our force. It doesn't make it any easier. But what it does, it allows a small movement to move the resistance a greater distance. So it multiplies our distance.
Is that it?
Nope. So again, if I set my lever up this way, I lift up my hand a small amount, how much does the object move? A lot. But I have to use a greater force.